in case of continuous control systems, where similar analogy, we have the Z transforms for the discrete time systems, and so we'll see that how this, what it means by is the response of this kind of systems, with respect to the time domain and the frequency domain, and how that affects design of controllers. That's the important thing which we'll see later. So when we are looking for the response of a control system, what essentially we are interested in is we classify the response of the system in two different steps. One is the transient response and one is the steady state response. So this would really mean that what is the initial nature of the response, that's what we call as the transient response, and what is the final nature of the response with letting the time settle down in an asymptotic manner. So and there are very good reasons why we actually classify such response. So for example, this is a typical RC circuit charging curve, right? So if you look at a RC circuit charging curve, you have we always know that finally the value of the charged capacitor is going to reach, almost near to the input voltage, right? So that's going to be the steady state, and initially we'll have a transient state response, right? So when we talk about the overall mathematical time domain response of the system, it can be divided like this into this transient and steady state response. So, and that's how it's defined, that any transient response with time approaching infinity, sorry, this should be t, is always going towards 0, whereas the steady state component is what is going to really remain. So if you look at the response of a control system, if this is the overall response, then definitely this e to the power minus 2t term is going to attenuate with time, and in the steady state response the value is reaching up to 1. Now for the purpose of system identification, there is a very well-known technique in dynamical system theory which is known as observing a system's behavior with respect to standard test signals. Now why is this important? Because if I give a standard test signal to a unknown block, right, and see what are the transient and steady state response, that tells me something about the nature of the transfer function of the block. So because because there are certain classes of responses, the overall response that I'm going to get is in most cases going to be one of those classes, and from that I can actually identify well what is the nature of this transfer function. So I believe these things you know, right? The standard test signals, like what is an impulse signal? It's a signal which has a value, some specific value, let's say a at time equal to 0, and at all other points is defined as 0. If it is 1, then it's a unit impulse signal. Can I consider these as known to everybody? Or if not, then we will go through this in detail. I just request to raise a concern if anybody is not familiar with things like impulse signal. Please let me know. Hello.
Yes, sir.
So I believe all of you have this background in Laplace transforms and basic transfer functions, right? Can I assume that? If not, please tell me. If there is somebody who is not having that background, please tell me.
Oh, excuse me, sir. I didn't have that in my first year.
Okay, but you had Laplace transform, right?
No, sir. I didn't. I think it may have been removed from the syllabus.
Oh, is it? Anyway, that would really mean that you have to read up a bit on Laplace transform. So it's one of the basic transforms on signals. There are quite well-known books on that. So I think that would be helpful for you. Okay, so we'll go through this, and maybe some of this is going to help you. But again, you must read it from one of the basic engineering mathematics books. Fine?
Yes, sir.
Okay, but definitely be in touch with us outside the class, so that if you need help, we can always provide that to you. Okay. So apart from these impulse signals, you also have this step signal. Like, so this is an example of a step signal. If a is equal to 1, then it's a unit step. So at t equal to 0, we have a finite value. Before that it's 0, and after that it's going continuing at that value only, right? Similarly, we can have a ramp signal defined like this, and a parabolic signal, and blah blah blah. Now, all these signals, these standard test signals, we can see that they are actually related by integral as well as differentiation, right? So if you are impulse, if you integrate it, you get the step. The step, if you integrate, you are going to get the ramp, and the ramp you can integrate to get the parabolic signal, right? And of course, we are familiar mostly with these Laplace transforms of test signals, right? So unit impulse Laplace transform is going to give you this value only. And for step, as we know that it's a constant value, so we'll have a bias in the denominator in the S domain, right? And similarly, you can compute easily from standard transformations what is the value of ramp and parabolic and all that. Okay. Now coming to this concept of transfer functions. So if we think of drawing the block diagram level picture of the control system in the Laplacian domain, it would look something like this, right? So we have the plant block. So as you can see, the plant block is what we call as the open loop gain, right? Because this is a transfer function which is in the open loop unless we close the loop by the controller, right? So let this be the plant block in the Laplace domain. So it's called GS. And then you take the output, let the output be CS, and it is fed back, right? And you have the feedback loop gain, right? So that's HS, and the output from the feedback loop. So basically you get the signal output from the controller. You are applying the control law, right? And you are generating a feedback gain here, right? And this you are, comparing with the reference, right? And that is generating an error signal which is going to the open loop plant gain, right? So this is a flow diagram of the control system with feedback in the Laplace domain. Now at each point, if we are going to sum up these signals, what do we get? So definitely I can write this BS is nothing but, this HS, there is a this blocks transfer function, right, in the Laplace domain multiplied by CS, right? So BS is HS times CS. Again, I can write this GS as nothing but what CS by ES, because ES is the input and this block is transferring it, and then the output you get CS, right? So GS is CS by ES, and definitely the error is nothing but RS minus BS, right? So with this set of equations, through a bit of transformation, what we can do is we can figure out what is the ratio of C by R. What the ratio of C by R is that C is the final output that I get, and R is the reference input of the system, right? So this ratio is what comes out to be the closed loop feedback gain, closed loop feedback transfer function of the control system. Okay. Basically, it means suppose now I draw a boundary over here, right? And think of this entire block, then what is the overall transformation of the entire block? It must be something which is equal to the output CS divided by the input ES, RS, and it works out to be, from the above set of equations, this CS by RS works out to be this G by 1 plus GH, right? So this G, which is the open loop gain, divided by 1 plus G, 1 plus A, 1 plus G into H, where H is this feedback loop gain, right? So this is your closed loop transfer function, given an open loop gain G and the feedback loop gain as H. Fine. So that would be the closed loop transfer function. Which we can always work it out given the open loop gain and the feedback loop gain. Fine. Now, once for any transfer function, once we look at the nature of the function, a lot of things actually can be derived from it. Okay. So, but to analyze that function, we need to understand this concept of poles and zeros of the function. So if we look at the transfer function, the poles are defined as the values of the Laplace transform variable s that cause the transfer function to become infinite. That is, for what values of s the denominator is going to be 0, right? So basically the roots of the denominator. if I take the denominator of a transfer function, set that to an equation with left and right hand side equal to 0 and solve it, whatever values of s I get are the poles of the function, and the zeros of the function are nothing but the values of s for which the numerator becomes a 0. That means, so sorry, this should be roots of the numerator of the transfer function. So this is basically what is going to evaluate the entire transfer function to a 0. Okay. Now, why are these important? Specifically the poles. The poles are going to be very important for in a system's transfer function because they are going to control what is the forced response of the system and the natural response of the system. So we'll see what it means. So suppose you consider this function s plus 2 by s plus 5, right? So if you work it out, you have a 0 at minus 2. Like we said, zeros are marked with these circles and poles are marked with crosses in the Laplacian S plane. Okay. So if this is a transfer function, what we can see is we have this pole at minus 5, right? Now, so when I am trying to compute the output with respect to an input that is 1 by s, 1 by s is the transfer function Laplace transform for what input test signal? Anybody?
Step response.
Yeah, so we are considering the unit step response for this transfer function and trying to analyze it, right? So with this 1 by s as input, we are trying to figure out what is the output, right? So output CS is nothing but 1 by s multiplied by this GS, right? 1 by s multiplied by s plus 2 by s plus 5, right? Now if you consider that 1 by s multiplied by s plus 2 divided by s plus 5, the output you can work it out like this, right? You can, in the output you can have two parts of that entire thing, right? You can write 2/5 of s plus 3/5 divided by s plus 5. You can write this thing 1 by s multiplied by the function, you can divide it into two parts as this plus this, right? Now if you transfer back to the time domain, 2 by 5 plus 3 by 5 into e to the power minus 5t, this is what you are going to get, right? So for this, so basically this is a time domain response of the system. This is telling you in what is the output in the time domain, right? So as you can see, there is one term without t and another term having the t, right? So one part is what we call as a forced response, which is without the t, and the other part is without the t, and the other part natural response is with the t, right? So essentially this natural response part is going to die down with time, right? And the forced response part is going to remain, right? Now, can you tell me what is the effect of the pole of the transfer function on this response? Anybody?
Stability of the system.
Yeah, but how is that getting reflected here in the output? So as you can see, the pole was at what position? It was at minus 5, right? Because as we said, the definition of pole is whatever is the value of s that makes the denominator 0. We had one pole which is at minus 5, that because s plus 5 is the denominator, right? So this, as you can see, the 5 denominator occurs here, and it is kind of controlling both these forced and the natural responses, right? So that's the influence of the pole on the output that we can see here. So this is what we can call as an example of a first order system because it just has one pole, right? So in a classical manner, so for the person who said you need some help on transfer function, I'm just stopping here. Shunandan, are you here?
Yes.
I believe we can provide him with this transfer function, some
Yes,
material on
we
that,
can.
right?
Yes,
Yeah.
yes,
Yeah.
we will definitely.
Yeah.
Yeah.
And also you contact us separately, okay? Because I think this part you will have issues. I'm not stopping here right now because for the sake of the class we will move on, but we'll help you in an offline manner, okay? Yeah. No problem. This is actually quite an easy thing, and it's an essential thing to know for any engineering student. Okay. So coming to this first order system, like I said, that any first order system is classically represented by this kind of a transfer function where you have only one pole, right? So now let's say you have this this first order system example 1 by st. and you put it with a unit feedback gain, right? So the unit feedback gain is nothing but this is your feedback, right? And there is a unit gain 1. That's why nothing is written here, right? So that would mean the overall transfer function is like we decided earlier, it is g by 1 plus g into h. G is 1 by st and h is 1, right? So it would be resolved to 1 by st plus 1, right? And from that we can figure out what should be the pole position. So as we can see, pole must be at s equal to minus 1 by t, because that is the value which is going to set this denominator to 0, right? So again, as you can see that if you take this output, right, and if you apply a unit step here or something, this is going to be 1 by s again. And just like the previous example, you can work out, or for example, here in this example, we are taking a impulse response. That means r is delta t. So that means in the Laplace domain, this is going to be 1, right? So for this system, if r becomes 1, right, now you take the inverse transform in the time domain, compute ct. So what you get is the inverse of this quantity, right? And that is going to give you this 1 by t e to the power minus small t by capital T. So basically the capacitor discharging curve, right? So similarly, you could have taken the unit step like I was saying, and in that case you can just compute another response. So it's just like you will in that case you will have a constant part along with this transient part, right? So unlike this one where you had just the transient part and the constant part was evaluating to 0, right? So this is how it goes. For a first order system, the response of the system can be plotted. Now as you can see, for the impulse response, it's going to be like this, as clearly can be seen from this equation, and we can easily work it out how this is coming by doing the inverse transform. And if I consider the input r as u, though that would be that is rs is nothing but, I mean, whatever is this value, if this value is 1, then nothing but 1 by s. So then when computing c, it would be this 1 by st plus 1 multiplied by 1 by s, and then you can resolve it just like we did earlier for the other case, right? And then we will have two parts in the response, a constant minus the transient part, right? So how is this curve going to look like? This system, if I check the output, how is this curve going to look like? Anybody?
So it will converge to 1 at t which infinity.
Right. So it's basically going to look like a capacitor charging curve, right? Because this natural response part is soon going to, I mean, this one is going to die down, and the steady state should be 1, right? So this is how it is going to look like. Now there are some interesting quantities here. If you remember, for this kind of a curve, we will have an initial slope. This slope is nothing but 1 by the time constant of the curve. The time constant means this quantity capital T here. Okay. So that means think that you don't know anything about the system. You are giving it an input, which is a unit step, and you are looking at the output, which is this, right? Now from this output, if you measure the slope, you get to know what is the value of T, right? So what and this what is this time constant really defined at? It's a 60. It is the time after which the value is going to be 63% of the final value. That's the definition of time constant. You can easily work that out. Why this holds, right? Because that's essentially coming from the value of E only, right? Now, similarly, there are two important concepts that can be defined. I mean, this value after which, I mean, it's so basically this is 1 by t 1 by a, right? Because time constant is 1 by time constant is taken by a. So this value is nothing but 1 by a. Similarly, I can have 2 by a, 3 by a, and like that at different points of time, right? So as you can see, we are writing two new quantities there, tr and ts, which we will soon term as response time and settling time, and we'll define what they mean. So this is it. Sorry, rise time and settling time. So the time constant is nothing but the time required for this function e to the power at to decay to 37% of its initial value, right? Now that matches, right? So this value is decaying, right? If this value is decaying to this, right, then the overall thing 1 minus this value is going to increase. So if this decays to 37% of its initial value, then the overall thing is actually rising from 0 to 63%, 1 minus 37 of the final value 1, right? Am I clear? So that's why if you look at this, you can see the slope, and from that you can figure out this value of a here, right? If it is e to the power minus at, from that slope you can figure out what is the value of a. It's just the inverse of the slope. So this is it, right? E to the power minus 1 by capital T times small t. So we look at the slope, and just the inverse of that is going to be this value of this t. Any questions?
No, sir.
Similarly, we can define another quantity, which is the rise time, which is basically the time required by the waveform to go from 10% to 90% of its final value. So here you see, you are looking at the response, right? And you see the time when it is at 10% of final value, that is, it is at 0.1, and at 90% of final value, that is 0.9. Take this difference, and this difference is, this is the time which we call as the rise time, and you can easily work it out that this is nothing but 2.2 times t, or 2.2 divided by a. T is the time constant. Again, is this clear? So
Yes, sir.
So all these quantities, as you can very easily understand, comes very simply by solving this equation only. That when this equation reaches what value, I mean, from that only I can get an estimate of this value of t, right? And so we have the time constant, we have the rise time, and we can also have what we call as the settling time. So settling time is nothing but it is the time after which the response rises to a point which is almost near to this 98% or something of its final value. I think it's so. Yeah, that means it is reaching within that. That means that is why we are saying it is staying within 2% of its final value. So up to the point where it is reaching 98% of its final value. So that's basically, as we said, it's this value 4 by a, right? And so from this, from the measure of the settling time also, I can figure out what is the value of a, and a is 1 by t, and from that I can say, well, this is a first order system with this kind of a response. So you can understand, right? Any first order system will have a response curve like this, subjected to a unit step signal, and looking at these values you can actually figure out what really is the characteristics of the first order system. Similarly, you can have a ramp response. You can design a ramp response with similar characteristics, a parabolic response with similar characteristics, and figure out how it works and all that. Very similar principles will work for a second order system. Now, what is a second order system? Something for which its response is dictated by not one pole, but two poles. Okay. So that would mean we can assume that since it's going to have two poles, that is why the this denominator of the second order system is going to be a quadratic polynomial, right? So you have terms based on s square, something with s, and something which is constant, right? Because there are going to be two poles. So this equation is going to give you two solutions for which this equation evaluates to 0, right? Now, why are we writing this in this specific form? Because we will soon see that this omega n and this term zeta are going to have some specific meanings. We will soon see that omega n represents the undamped natural frequency of the second order system, and this zeta defines what we call as the damping ratio, but we will define them later. I hope this is clear why we are taking a quadratic here, because it's a second order system. Its response is going to be dictated by two poles, and there is a constant value here, some constant whom we are writing as omega n square, right? So basically this is the system, and these systems, or this is the open loop function. You put it in a unit feedback closed loop, and that gives you this closed loop function, right? Now, as you can see, if this is your closed loop denominator, you can solve it to get these two pole positions, right? So the pole positions are at minus of zeta omega n, plus minus omega n square root zeta square minus 1, right? So that would really mean there are various possibilities now, right? So suppose your value of zeta is 0. If your value of zeta is 0, then what happens? Where are these going to be located? Well, so then the real part becomes 0, right? If the real part becomes 0, then two of these poles are both located on the imaginary axis, right? Now, in this case, the response of the system is going to be fully oscillatory. Like we have said that this is why we call this zeta as the damping ratio. Why? Because as you can see, this value of zeta is controlling whether the response is going to be damped to some constant value or not. Clearly, with zeta equal to 0, the output is not damped, right? So the output is undamped and it is going to be constantly oscillating like this inside the full amplitude range, right? So this is an undamped response. Now consider this value of zeta to be between 0 and 1, and when that happens, what we really get is, well, see, this is between 0 and 1. That means this part is again imaginary, right? Since this is imaginary, then we have two proper complex numbers, right? Whose real part is minus zeta omega n, and the imaginary part is like said, I mean j omega n square root of 1 minus zeta square, right? Plus and minus, right? So this is what we call as the underdamped situation because the value is between 0 and 1. So initially there will be an overshoot, this kind of a high peak, and then the response is slowly going to damped, right? Going to get damped. This is called underdamped, right? Now what happens with zeta equal to 1? With zeta equal to 1, your imaginary part goes off the book, right? And we only have minus zeta omega n remaining. So you have two poles at the same location, but they are all real poles, right? Now in this case, the response is going to look like this, which we call as critically damped, right? And when zeta is greater than 1, so then you see there is no imaginary part. This is also becoming a real part, right? Now with that becoming a real part, you have two poles, both of them on the left half plane. And as you can see that the response is going to be like this. We call this as overdamped. Why overdamped? Because there is no oscillation. So this is overdamped, critically damped, underdamped, and undamped. So what kind of system do you really want? You don't want an undamped system, because then, well, the system is not really settling down towards a reference or some value around which you want the output to be, right? So you should not have a system where there is no damping, right? Zeta should have a non-zero value. Now question is, it is very difficult to get a system which is critically damped, right? So getting an absolute value of zeta equal to 1 is very difficult, right? So we consider this as some scenario we can never achieve, that is, it's critically damped to perfection, right? Overdamped, the problem with overdamped would be that, well, this rising it and finally settling towards the value may really be slow, right? What you will really like to have is something like this, where there is the system's output rises fast. Now this is why you may be wondering why I'm saying this, but now if I show these two pictures one side by side, it may be clear. See, in the overdamped case, the system's response is not rising very fast, it's rising slowly. In the underdamped case, the system's response is quickly catching up with the output, right? As we said, there are two important things in the control system, stability and performance. We want it not to deviate too much from its reference. And I don't want it to deviate away further and further with time with respect to the reference. Also, I want it to be very high performing. That means it should be approaching that reference very fast, right? So that's what happens in this underdamped case. It's approaching the reference very fast, then it overshoots the response of the reference. Then it should come down and slowly it is going to settle down like this, right? So this is the kind of response we'll really like for the system to have. And that's how, and you see that this has a dependency on both the value of this, zeta and omega n. What is going to be the top value here and how fast this is going to rise depends on both of these quantities. And as you can see, there are also going to be oscillations here, right? Oscillations are going to be damped, but the oscillation frequency is controlled by omega n. That is why it's the natural frequency of the system. Omega n denotes the frequency of the system. And the amount of damping these successive peaks are going to have is being denoted is actually going to be captured by zeta, which we will soon see, right? Another important thing to you to observe is in all these cases, you see the poles of the system are all located on the left half, right? So we'll soon understand that this has something to do with the stability of the system, right? When the poles are all on imaginary, it's basically marginally stable system. It's not stable actually. And in all the cases, the poles are located in the left half plane, and that's why the system is going to be stable. Because if the pole gets to the right half plane, what really happens is your undamped oscillations are slowly going to build up instead of them remaining the same in the undamped case or going to be slowly attenuated in the underdamped case. They are going to build up continuously, and with this continuous build up, the system is eventually going to be unstable. So we'll soon see these things. So this is a final summary here. You have this undamped, this is underdamped, you have critically damped and overdamped. As I said, overdamped is not a good thing. I mean, well, it is stable, but the response is slow. Underdamped is what? Where well the response is fast, and this is also stable. But we have to control the amount of overshoot. It should not be too high and all that, right? Now, we have understood that well for this undamped case, these are the pole locations. The real part is minus zeta omega n. The imaginary part is something like this, right? Now, as I said, that both the quantities zeta and omega n controls the response. Now, this is what we call the damping curve. So, if you take the undamped response and connect all the successive peaks of this sinusoidal, you see that the peaks are reducing, and the amount by which they are reducing is basically same as this damping quantity zeta, right? And this frequency of these oscillations is basically same as that frequency quantity omega n. So as you can see, with different values of damping, you are getting different possible waves. But what is the same thing about these waves? Can somebody say?
So the
Time period.
The omega n is same, right? So when I'm drawing them, you can see the damping is different. That is why the waves have got their peaks different, but all of them have got the same frequency. That is why they are crossing the zero line almost at the same time. Now, for this kind of a wave, this typical second order response, we can actually create some of these definitions. So just like earlier, we can have a definition of a rise time, right? This can give me the time constant. This can give me the rise time. This is what we call as the maximum overshoot, MP, with what is the amount it deviates maximally from the unit impulse. And the amount of time to get the overshoot is TP. And then we can define a settling time, just like earlier, is the time by which the response goes within 98% of the final value, right? So the deviation is within 0.02, or there are some alternate deviations where definitions where they say the deviation is within 0.05, right? So that's your definition of settling time, your definition of rise time. Rise time, as we discussed, it should be at some percentage of the final value by the time 63 or something that was there, right? And then you have the definition of maximum overshoot, right? Now, yeah, so we have all these definitions here. Delay time, the time required for the response. These are all specific to the second order system here. TD, the time for which it reaches this value, which is 0.5. That means 50% of the final value. And similarly, rise time is the time required for the system to go from 10% to 90% of the final value. Just like we discussed earlier, it goes from 10% to 90%. Okay. And but that is for the overdamped system. And since this is the underdamped system we are drawing, is basically from 0 to the 100%. If you remember the earlier picture of the first order system, there the rise time definition was basically 10 to 90. But here we are saying that, well, with second order system, we have all these possibilities, right? We have an underdamped response, overdamped response, and all that. And among them, if you remember, the overdamped response is what? Which looks pretty similar to the first order response, right? That is why for the overdamped response, the condition of the rise time remains same, which is 10 to 90. But for the other case that is underdamped, we are making it different because the response curve looks different for the underdamped system, and we say it's 0 to 100%. Okay. The other is peak time, that is the time for which is required to for the system to get the maximum overshoot, right? Now, a question here: Can you tell me how to calculate the peak time for a transfer function as defined for the second order system?
We can find the derivative and
Exactly.
equate that to 0.
So we'll take it, multiply with 1 by s, that is the unit response. So that gives me the overall response of the transfer function. So and then we'll do a derivative and we'll see that what is the value where it reaches the peak, right? Now if you do that, this would be your solution. Now as you can see that this solution again depends on both omega n and zeta square, right? Now similarly for the settling time, the settling time definition in this case is like this, that it like we defined earlier, from the start up to the time when it reaches 2% to 5% of the final value. Now if you consider the 2% criteria, the equation would be 4 by zeta omega n. If you consider the 5% criteria, it should be 3 by zeta omega n, right? Now consider this. Suppose you have a second order transfer function block, you don't know it. You give it an this unit impulse and you get this kind of a curve. From this curve, will it be possible for me to know what is the transfer function? Anybody?
If we know the values of TR, TP, then we can find them.
Yeah. So if we can check this curve in a let's say an oscilloscope, or if you are doing in MATLAB, then in MATLAB, then we can measure all these quantities, right? The rise time, the peak, the maximum overshoot time, and the settling time. And we have all these equations, right? The peak time equation is there. We have the settling time equations are there. So we get 2 or 3 equations, and from which you have to solve and get two quantities, zeta and omega n. So that can be done, right? And once you get zeta and omega n, you have the transfer function. Okay. Now this is what we have been saying, that well, with the position of the poles and zeros, how the responses are going to change for the underdamped system. Now suppose the poles are going, I mean, see, if the value of this zeta is going to increase, right? And let's say omega remains same, then what is going to happen? So with zeta increasing, the pole, this pole is going northwards and this pole is going southwards, right? So what that would really mean is that you have higher damping, right? So as you can see, that's really true. This is the curve with for the case 1. This is the curve for case 2. This is the curve for case 3. So as you can see, all of them have the same envelope, but with higher damping. 1 minute. If I just look back into that equation once, yeah. So this is what is controlled this, right, by minus zeta omega n. So this is the real part, right? Now when we are saying that, well, this minus zeta omega n is there and these poles are moving like this, the minus zeta omega n part is fixed, right? So that's the real part. What is really changing is the imaginary part. Now let's once again look into the imaginary part. It's basically this, right? Omega n times square root of this, right? So if this part, I mean, when I say that the poles are going far apart, what does that really mean? That does it mean that zeta is increasing or decreasing?
Increasing.
So you see, if zeta is going to increase, then only this imaginary component's value is going to increase, right? So that's what is happening. So if you have these things going apart, that only means that the value of zeta is increasing, right? Now if zeta is increasing, that means your value of damping is increasing, and the effect can be seen here, right? So you see, you have this value of the damping going higher, right? I mean, with more damping, what is happening? You are getting the response faster, but it's soon getting damped. So the second peak is going down, right? And again going down like that. But for all of them, the envelope is, sorry, I think, 1 minute, please. Yeah, I think, sorry, this second curve is what should correspond to this situation. Because with higher damping, you have a more damped scenario. For example, this. Yeah, sorry. Consider this second curve for this picture actually. So what's happening is you have these poles going apart, and Ipshita, Surandan, hello. Please help me remember after the class.
Yes. Sorry. Yes.
Just help me remember after the class. This slide I must change actually.
Okay.
There's an inconsistency. Yeah.
Yes.
So with your poles going apart like this, I mean, we're just following the logic here, as simple as that, right? What is happening is your zeta value is increasing, and that's the only way. With the same frequency, your poles can start going apart, right? Now with your zeta value increasing, what's going to happen? Very simple. Your frequency will remain the same, and your damping value is going to be high. And you can see that it's clearly visible from this second curve actually. In both cases, your frequency is the same, but as you go from 1 and 2, and maybe even if I have been plotting a 3, what would be happening is your damping is going high. With higher damping, you have lesser amount of overshoot. So in 1, you have higher overshoot, and then again a small peak like that. With 2, you have a smaller overshoot, and then a smaller peak with respect to 1 like that. Is this clear to everybody?
Yes, sir.
Sir, I think the frequency is not constant here. Like,
no, the frequency is constant, because you can see that all the waves have the same frequency in this picture. They are doing the crossing here almost at the same parts. What? Let me just.
Go back to the previous slide once.
Yeah. Let me just see the equations once again. I think I am missing. This is what happens when you don't have the board. Okay, so we have two things, right? We have the zeta omega n and the omega n times square, I mean, this thing, right? Okay, now let's say the picture is that your poles are moving to the left on the imaginary, on the real axis, right? I mean, what are we really trying to say here? Yeah, your poles, let's say they are moving to the left. Okay, I got it. Here we are saying in the second case that the poles are just moving to the left. That means your imaginary part is not changing and the real part is changing. And the way that the real part is changing is just by keeping the frequency as same, but changing the value of the damping. Is this clear to you? See, if I keep the frequency same, but increase the damping here, no, but with that, what is going to happen is both these are really going to change. Both the real and imaginary part is going to change, and that would really mean, okay, I think the point that we are trying to make here. No, okay, now I understand how why yeah. Let me just brief this part once again. What we are really trying to tell you here is, how is the response affected if I am just going to alter the real part and if I am just going to alter the imaginary part? Okay, now please look into this. If I alter the real parts just like this, I mean, they are going left hand side like this. Okay, I mean, it's not really the thing that, well, how much, what is the frequency and what is the value of the damping? We are trying to say that this real part is actually telling you what is going to be the amount of damping here. Yes, you had a question here. Anybody? Somebody was saying something.
Sir, like I usually, sir, like we have control systems, so I remember we used to do it, take it to the extremes. So, sir, if the real part is zero, we know that it is oscillatory, and if
Yeah,
it becomes more imaginary, that is the amplitude of imaginary part increases,
exactly,
then the
exactly,
frequency
exactly. We are coming to that. We are coming to that. What we are trying to say here is, if you keep the real part increasing, see, if I say that these are the poles and I am moving the poles like this to the left hand side, then what is really going to happen? Your imaginary part is constant and the real part is increasing. Am I correct? Just look at this picture. Hello?
Yes, sir.
Now that would really mean you are, since the imaginary part is controlling the natural response, okay? And if you are increasing not the imaginary part but the real part, what you are doing is you are increasing the damping of the system. Okay, this picture is actually correct. I mean, when I did it, it must have been correct. Yeah. So since you are not modifying the frequency of the system, that is not modifying the imaginary part, but only modifying the real part. So if you check the response of 1 and 2, you will have the same frequency, but the damping is increasing. So the more I shift the poles to the left hand side without changing the imaginary part, I am just changing the damping. I am making the damping of the system higher and higher without changing the frequency. Is this fine? Hello.
Yes, sir.
Now consider the figure A here, right? If you move the poles like this, that means you just move the poles apart from each other. So this was initial position of 1 and 1. Now this is the initial position of 2 and 2, like that. That means you are keeping the real part fixed and you are just moving the imaginary parts higher. That would really mean, well, the damping is same, but what is really changing is the frequency. So you see, initially 1 was this. This was a smaller frequency. Then the second response has a higher frequency. The third response has a higher frequency. But what is really constant about all these curves? Anybody?
The envelope.
The envelope. And what is really controlling the envelope?
The damping.
Fine. So that's the point we have been trying to make here. Sorry, I got confused in between. I was trying to relate this with both the values of j and omega like that. That's not what really we're trying to say here. We are saying that the overall value given by j and omega, they are tweaked in such a way that, let's say, you have the real part as constant and the imaginary part as increasing. Okay, the effect of the imaginary part is solely on the frequency response, that at what frequency the wave would really be oscillating, whereas the damping remains same, right? And similarly, if I am making the case that I don't change the imaginary part but just the real part is solely controlling the overall damping of the response but not the frequency, right? So the overall damping of the thing is going to change like this. I hope now this is clear. Earlier I was trying to wrongly connect with the value of j and I mean value of omega and the value of the damping, but this is a picture drawn keeping both of them together in such a way that the real part is either changing and imaginary is constant, or imaginary is changing and real is constant. Because as we can see that this whole thing, this j omega, I mean this omega eta together is what is giving me the damping, not a single of them, right? I mean what is giving the actual position of the real part. And similarly, their combination is something in a different possible way, that is omega n times this. Combining them in a different possible way is actually telling me what is the imaginary part. And now we are saying that, well, let the real part remain constant and imaginary change, the imaginary remain constant and real change, then what happens? But of course, this is just to tell you how, if the poles change in only one component, how the system response is going to change, right? This is just telling you that much. This is not really connecting you with the exact value of, this is not really telling you that, well, I am changing omega but not changing zeta, or I am changing zeta and not changing omega. This is not what it's telling you. This is telling you, if they are combined in such a way that the entire real part is same and the imaginary changes, or the reverse, the entire real imaginary is same and the real changes. I hope now this is clear. But now come to the actual thing. Suppose I am going to change the values of zeta and omega. So all practical purpose, what is going to happen, right? They are going, the real and imaginary parts are going to change together like this. Got my point? So suppose you fix omega and you are changing zeta, it will have effect on both of the real and imaginary parts, right? Or in the other way around, if you change zeta, if you have, I mean, omega and only changing, again it will have its effect on both the values, right? So for all practical purpose, the values are going to diverge like this, and the effects will come like this. Well, if they keep on diverging from 1 to situation 2 to situation 3 like that, what is changing is both, I mean, the imaginary and real, both parts are actually increasing. So that would mean, well, you have a higher value of damping, and also you are going to have a higher value of frequency as you move from situation 1 to situation 3. Is this clear?
Yes, sir.
Why do you call this as the constant damping scenario? Is this, can anyone tell me what we are really doing? So constant damping scenario means we are saying that, well, keep zeta same and change omega n. But that would really mean what? Since you are changing omega n affects both the real and the imaginary part, right? So the poles start moving diagonally, and accordingly it has its effect both on the damping and the omega n part in a monotonic way, and accordingly you have a higher frequency as well as a higher damping as you move from situations 1 to 3. Okay, so that would be a summary of this kind of responses, and then let's move. Let's just move on to further topics, and the thing which we like to talk about is stability of the system, right? So, what do we really understand as a stability of a system? Anybody has any comment on that? Not I mean, I'm not asking you a definition of stability. I'm just asking you intuitively what we think of what is stability. Hello.
So the stability, intuitively speaking, it's basically a state where it will stay in that state unless an external force or external thing is applied to it.
Wonderful. So basically, a stability is a property which tells me that, well, the system is in a state, and if I perturb the state, how well the system is going to respond. Is it going to be in that state? Is it going to come back to that state, or is going to never come back to it, and all that, right? So in general, we'll call a system as stable in the from the transfer function point of view if the natural response is going to be 0 as time approaches infinity, right? And if the system is unstable, if the response is not suitably damped and the response keeps on increasing and approaching infinity as the time approaches infinity, right? And the system is considered marginally stable if the natural response remains constant or oscillates within a bound. That means the response is never attenuating. So these are the situations. So this, let's say for a transfer function you give an input, and this second thing is what we want from everything, right? This is an undamped response. I mean, sorry, this is an underdamped response, the one we have been studying, right? And this is what we love, and this is what we desire of all control systems, where we want that the response should be underdamped in such a way that we are able to tune the values of this zeta and omega n so that we can control where is the peak, where does it settle, how much does it rise, and everything, right? Third one is also stable, but what is it? What kind of stability, what kind of response is this? Anybody? We have already started this a few minutes back. Hello.
Overdamped.
Exactly. So this is an overdamped response. I mean, the good thing is it is stable. The bad thing is, well, you see that it's not performing well because it is taking a hell lot of time to climb to that level of the reference, right? The underdamped system was climbing much faster, right? So for most systems, we like to have it behaving like this under our control of, I mean, achieving settling time and maximum overshoot requirements. This is called marginally stable because as the definition clearly says that there are oscillations, but the good thing is the oscillations are always bounded by an upper and lower value, that upper crest and lower trough, right? It's not going unbounded. This one is unstable because it's continuously rising. So this is like you see the frequency component is positive 0 because there is no it's just keep on rising, right? And this is also unstable because you have a frequency component, which is that means that means the poles have an imaginary component, right? This doesn't have an imaginary component, but the decay component is not here, right? In this fifth case, your decay is not a positive decay, right? So you really do not decay, but you keep on increasing. In the last one, you do not only have a positive decay, plus you have an imaginary part. So you have an oscillating response, and that oscillatory response envelope is going to keep on increasing. So this is fine.
Yes, sir.
Now, if we try to define that, well, what is stability and all that, one standard thing is what we call as bounded input, bounded output stability, that the system's response, if I give it a bounded input, so these are all step response curves. If I give it any bounded input, the system is guaranteed to have a bounded output. So that is typically the concept of stability most of the times we are interested in, right? And we have already talked about that, well, if the system is stable, we have seen that how it depends on the position of the poles, right? We have seen that, well, if the poles are located on the left half plane, depending on the location of the poles, we can have different responses. For example, if it's fully on the left half plane with no imaginary component, it should be like this. Left half plane with an imaginary component should be this. If it's located on the imaginary axis, there is no left half plane component there, so there is an undamped response like this, right? So you can see that for different left half plane pole locations having roots which are complex as well as real or purely imaginary, you can have different responses, but all are stable responses. Whereas if you put the pole on the right hand plane, all these are going to be unstable responses. So definitely this tells me that how do I analyze the response of a transfer function? I look at the transfer function, see where the position of the poles are. If the poles are all in the left half, then it's stable. If the poles are in any pole is there in the right hand, it's going to drive it to an unstable situation. And if the poles are all on the imaginary axis and there is not a single pole on the left half plane to push down the response, then it's going to be marginally stable, right? So these are the conditions. I require that all poles will reside in the left half plane, and for doing a stability analysis of the system, I will do a look at the transfer function. I will see what is RS, that is the denominator polynomial, and all coefficients of the denominator polynomial must have the same sign. So that's a necessary condition. But the necessary and sufficient condition is all the poles must have a real part, uh, which is all the poles must have this that is going to reside on the left half plane. Now, how do I really analyze this? Well, very simple. You take this polynomial, the denominator, and you solve it out, see the location, right? And see whether they are located in the left half plane or not, right? That means the poles must have a negative real part. If they don't have a negative real part, that means they are not really located in the left half plane, right? Now, there is also another way to analyze it. Well, you have looked at the system, and like we said that for the system, we should be able to convert it into this kind of a generic form, the state space form, which is x dot equal to ax. If you remember in the previous class, we have been talking about the system representation with x dot equal to ax plus bu, where u was the control input. Right now, we are not talking of a system with a controller, but let's say that so there is no control input. The system just has the state variables and the system is moving about with the state variables. So then it should have a representation like this. Now the second thing is, even if the system has a control input, finally with overall the system with its controller, overall I can bring it to a final closed loop transfer function where I should be able to write it like this in this form, right? With this x dot equal to x form, right? Now, well, earlier I have been talking about transfer functions, right? But now suddenly we are talking about the state space representation, which we discussed in the previous lecture. That well, all the system state variables are known. Take the state variables and write it in such a way that the differential of the state, the time differential of the state variables are made to relate with the not the state variables and their coefficients, right? And in that case, what the matrix A we get is called the state space matrix. What are the poles of this system? Had we taken the system in the Laplacian domain, the poles are like we have discussed earlier. Now, once we take the system in this kind of a state space representation, the poles are again going to be nothing but the eigenvalues of this matrix A, right? So we can again check in this way that if we can write the system equations in this form of x dot equal to x, you figure out what is the matrix A, check the eigenvalues and see whether the eigenvalues have got negative real parts or not, right? If they have this now non-positive or negative real parts, it's a stable system, right? So this is how the stability of linear systems is analyzed. However, this is not the technique for analyzing nonlinear system stability. We need other techniques for that. We are skipping it for now. We'll come back to this topic later on in this course. So I hope now the concept is clear that you are given a system, you in let's say in the state space form, that is x dot is ax form, or in the transfer function form, and you have to find out what is the stability situation of the system. You can work it out simply by looking at the pole positions, right? So today in the tutorial, we will just take a few example systems and see how it can be worked out like this, and then we'll go forward. Okay. So with this, we'll be ending today's lecture. Okay, so I think for those of you from E or EC, most of these things are already known, and after the scheduling part, maybe you are getting a bit of bored. But anyway, for the overall class, we have to do this. After this, we'll have also one lecture on basic control design, which may be known to you. But after that, whatever topics would be coming would be the advanced topics related to more different ways of control design and artificial intelligence techniques for control design and the secure control issues and all that, which maybe will be the new things. And also we'll discuss how the effect of real-time scheduling comes on controllers. We have studied real-time scheduling, we have studied Canvas scheduling, we'll be soon seeing how all these things jumble up together. So how the control design and its performance really links up to scheduling, how a bad scheduling can kind of make the control system go bad and all that. So we'll soon see all those things. Okay, so with this we'll end the lecture and we'll have the tutorial starting. Anybody has any question? And then this is the time to bring it up. Hello.
Yes, sir.
Yes. Okay. Okay. So Shunandan, shall you start the tutorial?
Yes, we will. Yeah, we'll
Okay,
stop the
so
recording and we'll start the tutorial. Yeah.
I am unsharing the screen then. Thank you.